All right, so section 3.1. We're going to become owners, if you will, of the Plant a Seed Company. Okay? And our product that we are producing is something called a planter box. Now, a planter box is just that. It's a box that plants go in. Okay? All right? So what's going to happen, and unfortunately for those people watching the screencast, they can't see this, but what's going to happen is we are going to be cutting out from a rectangular piece of copper, we're going to be cutting out the four corners. And when we cut out the four corners are going to be the same. Okay? So we cut out the four corners here. Oops, that went a little too far. Okay? And then this one, and then this one. And then what happens is then we're going to bend that up and makes our box. Okay? Alright? So that's how we are producing this box. We've got a big old piece of copper. We're going to cut the corner, and then we're going to make a box. We're going to use a metal bender, and we're going to bend that up, and we're going to create the box in that fashion. Okay? Now, the nice thing about Plant a Seed Planter Company is that we are customer friendly. Okay? Whatever the customer wants, we will produce. Okay? Within reason. Okay? Alright? So, what I would like you guys to do now, after we'll do one of them together, okay, is I want us to fill in this chart. Okay? We're going to start with the height we don't know. The width start was 12 inches. The length start was 18 inches. That's from our piece of copper. It's 12 inches wide and it's 18 inches long from our piece of copper. Okay? Alright? So, let's do 1, 2, or 3. I don't care what. Pick it. 3? Okay? So if the square corner side length is 3 inches, so I'm going back up here. Let me see if I can get them all on the same page. Perfect. I can get them on the same page. So I'm cutting out 3 inches there. And I'm cutting out 3 inches there. And I'm cutting out 3 inches there. And I'm cutting out 3 inches up there. Okay? So if I cut out 3 inches, then that means then that my height, when I fold it, is going to be how much? My height of my box is going to be what? 3 inches. Okay? So the height of my box is going to be 3 inches. What is the width, then, of my box? It is not going to be 12 because it started at 12. And then I cut out 3 on this corner and I cut out 3 in this corner, so that leaves me with 6 inches. Yep. What is the length of my box? 12 on that one, because you cut out 3 on each end, so that we're taking 6 off, so 18 minus 6 gets me 12. Now, my question to you is this. Volume. You guys all went through geometry. When you were a tree, okay, how did we find volume of a box? Length times width times height. So the volume here is length times width times height. So what is 3 times 6 times 12? 216. And we're not going to worry about labels today because the labels are on our columns. Okay? All right? What I would like you to do now in your shoulder partners, and for those of you watching at home, you could pause the video right here. Okay? I want you to fill in the rest of that chart. Go. And we're back. All right, so your chart should look like this now. Okay? So if I don't cut anything out, that gives me a height of 0, that gives me a width of 12, that gives me a length of 18, which gives me a volume of 0. Okay? If I have a 1-inch cutout, that gives me 1 inch for my height. That means I'm taking 2 inches off my width, so that drops that down to 10. I'm taking 2 inches off my length, so that drops that down to 16, which gives me a cubic volume then of 160. If I have a height of 2, then that's taking 4 off and 4 off, which gives me a cubic volume then of 224. If I'm taking 4 off, that means, or if my height is 4, I should say, that means I'm taking 8 off, so that would give me a width of 4 and a length of 10 for a volume again of 160. If my height is 5, that means I'm taking 10 off of each dimension, so that would give me a width of 2 and a length of 8, which would give me a volume of 80. If I'm taking, or if my height is 6, that means I'm taking 12 off of each side, which means my width is 0, my length is 6, my volume is 0. If I'm taking 7 off, or excuse me, if 7 is my height, that means I'm taking 14 off of each side, which means my width is -2 and my length is 4, which gives me a volume of -56 cubic inches. What seems to be the problem with that? I can't have a negative volume and I can't have a negative side length. Yeah. Okay. So that one is probably not going to fly at the old Plant-A-Seed planter company. Okay? With me? Okay? I'm going to skip this last row until after we get some of the wonderful patterns that we see in it. Okay? So, talk to me, ladies and gentlemen, what patterns did you see in the table? As what?
As the corner side length.
Okay, so the corner side length is also what? Corner side length, or corner side dimensions, we'll say, is equal to the height, right? Okay, so now knowing that, you can say then that as the height increases by what? What was the height going up by? The height was going up by 1. Both the width and the length did what? Decreased by how much? So as the height went up by 1, the width went down by 2. And the length went down by 2. Because we were cutting stuff off of those dimensions. Okay? So based off of that, let's go back down here. Whoa! Slippy fingers. let's go back down here. So this, what did you notice about these first two columns? They're the same. So if I'm taking h off of each corner, that means the height of my planter box is h. Okay. What about, there it is, now I can see it. What about the width then? 12 minus 2h, because I started with 12 inches, and then we subtracted off 2 inches every time, because we have to take from both of that side's corners. Okay? What about the length? 18 minus 2h. Same pattern. Okay? We'll get to volume later on. Okay? All right? Any other patterns that we saw that I need to make note? Length is always 6 inches more than the width. Anything else? My last class came up with these two, that when you had one of your dimensions equal to 0, that gave you a volume of 0. Okay, so if one of your dimensions, so for instance in the 0 line, the 0 height, the 6 line, okay, had volumes equal to 0, and if we would have kept going, the 9 line would have had a volume of 0 too. Okay, and the other one that they saw was that the volume increases to h equals 2, and then it decreases. Okay, so our volume was going up, then it's decreasing, decreasing, and decreasing. Okay? Right? Good with that one? Okay? Now, what I want you and your partner to do is I would like you and your shoulder partner to answer questions 2A and 2B at this time. And we're back. Okay, so what is the largest size square corner? The largest corner that I can cut out is what? 5. Is h equaling 5 inches. And that gives me a volume of what? 80 cubic inches? Okay. Now, conversely, okay, let's take this one a little different direction now. What was the largest box that we produced? The largest box was what? Had a height of 2. And that gave us a volume of 224, right? Okay, so there's a difference there. Okay, it was asking for the largest sized corner that we can cut out, not the largest sized box that we produced. Okay, but we got them both there. Okay, question B then. What is the relationship between the size of the corner and the length and width of each planter box? we actually answered that already. The corner was h for a dimension, right? The width, then, was 12 minus 2h, and the length was 18 minus 2h. Okay? We answered those when we were looking at our patterns. Okay? Tricky lens. Okay? With me? Fantastic. Moving on to the next question. Question C says, now, write a function v of h to represent the volume of a planter box in terms of the corner side h. Okay? What did we say volume was? Length times width times height. Okay? So the volume of my function, or the volume of my planter box, is going to be what? H times 12 minus 2h times 18 minus 2h. Excuse me. Okay? Length times width times height. Okay? Now, what I would like you to do is I would like you to follow along with your graphing calculator. Because what we're going to do now is, here in question number 4, it's asking us to graph this on a graphing calculator. And just because we're screencasting this one today, we're just going to walk through it. In the last class, I had them graph it and all that fun stuff. So, couple of notes here about what's going on here. First off, these here are the x, min, and max and the y min and y max of the window that we are going to be graphing that on. Okay? So when you see that, this is what's called interval notation over here. So this part right here is my x min, my x max, my y min, my y max for the window that I'm going to look at this on my calculator. Okay? One other crucial thing that we have to do in order to graph this on the graphing calculator is we need to change our h's to what? We got to make them be x's so that we can see it on our graph. Okay? All right? So, I would recommend that you start brand new on a brand new page, because who knows who was using that calculator before you. Okay? So here is a brand new page. Oh, there it be. Okay? So now what we're going to do is we are going to type in our function. X now, instead of h, times the quantity 12 minus 2x times 18 minus 2x. And I put both of those in parentheses, and I put a multiplication symbol between them. Okay? Now, in order to see this, I'm going to hit enter. There it is, but that's not the window that I want to see it on. So I'm going to go into Menu, Window and Zoom, Window Settings. So it wanted to be -10, yes. Oops, one too many. And then it wanted us to go up to 15. I like to go by 5s there. Okay? Just because. My y minimum was -400. My y maximum was +400. And I'm going to go by 50s there. Okay? So that's my window. Now when I hit enter, there I see my function. Okay? So now I have seen my function. Now what I am going to do for us is I'm going to put that back into here. Riveting internet watching here now. Okay? And so now it's asking us to describe the key characteristics of this graph. What can you tell me about this graph? It's not a quadratic, no. So it doesn't have a vertex, it doesn't have an axis of symmetry, it doesn't have concavity. So that's off the table. There's 3 x-intercepts. What's another word that we call x-intercepts? Zeros. What's another word that we call them? Roots. What's another word? Answers. Do we say solutions? Okay. So we have 3 of them, right? Okay, because it crosses in 3 spots. Fantastic. What else do we see? One y-intercept. Oops, I don't like how that's spelled. How many y-intercepts will we normally have? 1. Okay, yep, normally we'll just have 1. Okay. What else? Let's relate it in terms of our problem. What does this blue curve, what does that blue curve represent? It represents what? The volume of the boxes. So in terms of our problem, yeah? All still good, right? All still good? All still good? But what about down here? No good down here. Why not? Negative volumes, right? Okay. So in terms of this problem, the red is possible. Now, my question to you is this. What about way over up in here? What about all of these? Here we got positive volumes again, right? Can I get those dimensions though? No, because this is like 10. Right here is 10, right? Can I get a height of 10 on my box? That would mean I'd be cutting out 20, right? Which means my width would be -8 and my length would be -2. So that's not possible. So this is the only applicable part to our problem, that which is in red. Okay? Let's go a little less high tech, if you will. A little less in depth. Looking at this graph, what can you tell me about this part right here? What does that kind of look like if we couldn't see anything else? It does not look like a parabola because it's not symmetric, because this side over here is flatter than it is over here. So it does not look like a parabola. It looks like kind of a hump, doesn't it? Okay. Okay. So this function has one hump. Right? And with a hump comes the Humpty Dance. With a hump comes what? What's up there? Not a vertex. It's not a parabola. It's a maximum point. Okay? With humps come maximums. This function also has a what? A dip? A valley? Whatever you want to call it. And with dips and valleys comes a minimum. Okay. Those are some pretty good characteristics of that graph. Now, what I would like you to do, actually we'll do it together because it's worked off the calculator. So we can find that maximum point, okay? Because here in part B, it's asking what is the maximum volume of the planter box. Well, what's going to happen is we can use our calculator to its fullest, okay? By going into the menu of the calculator, and I want to analyze my graph. Whoa! Look at what number 3 is. It's the maximum. I can find the maximum of it. Now, I will tell you this, that you do not have to be very precise with your maximum. What's going to happen with this line right here, this dashed line that's showing up there, is we're going to expand that out. And it's going to give us now I can do this one of two ways. I can just go to the right or to the left, whichever way I'm going, and notice how that maximum is coming along. I don't have to try and be so precise and so narrow with that range of values. I can go over as far as I need to go, and then once I hit that maximum, notice how then it gets locked in. Okay? So a lot of students try and be so precise, and they make their like box that we just did like that wide. Okay? And they try and say, well, the maximum's somewhere in there. You don't need to be that precise. You can be very broad with that. And you can add in, and then let the calculator do the work for you. Okay? So this now has a maximum of okay. So it has a maximum value at, or the maximum point I should say, is at the point 2.35, comma 228. Okay? So what does that mean? That means then that the dimensions of that planter box are 2.35 inches tall by 7.3 inches wide by 13.3 inches long. Okay? 2.35 times 2 is 4.7. 12 minus 4.7 gets me 7.3. 18 minus 4.7 gets me 13.3. So there's the dimensions of the box, and it has a maximum volume of 228 cubic inches. Okay. Looking at my function v of h, if I look at the blue, so I'm looking at this picture of this graph that's up here yet, okay? If I'm looking at that particular picture, and then I say, what's the domain of that function? What are the different numbers that I can put into that function? I can put positive numbers into that function, and I get out an answer. I can put negative numbers into that function, and I get out an answer. I can put 0 into that function, and I can get out an answer. So the domain of that function is all real numbers. Okay? There is no number that I can't put into that function. Okay? Now, in terms of the problem that we're doing here at Planta Seed Planter Company, okay, we have some issues though with any kind of number, right? I can't make a box that has negative height, correct? So the lowest that I can go in terms of my Planta Seed Planter box, or excuse me, our Planta Seed Planter Company, okay, the lowest that our domain can go is 0. But if we have a box that has height 0, what really do we have? Don't fall asleep, because I will call you out on the internet. Okay? So if I have a height of 0, it's just going to be a piece of copper yet, right? So do I really have a box? No. So are we inclusive with 0 or are we exclusive with 0? Exclusive with 0. So it's going to be from 0, okay, up to what? Oops, I shouldn't even go that far yet. Up to what? This was 0, this was 6, and this was 9. So we're going to go all the way up to 6, right? But are we going to be inclusive with 6 or are we going to be exclusive with 6? We're going to be exclusive because 6, according to our chart, gave us a volume of 0. It's very hard to plant a seed in a volume of 0 type of situation. Okay? Now, this is the inequality way of writing domains and ranges. We'll get to range here in a minute. Okay? The interval way looks like that. Parentheses in intervals mean exclusive. Brackets in interval way mean inclusive. So you're including that value in it. If you have a parenthesis, you're going infinitely close to it, but not including it. Okay? So, range now, that's what's outputting from my function. So after I put all these numbers into it, my range here is going to be, again, all real numbers, because my function here is going up. Oops. It's going up and to the right, and it's keep going, and it's going down and to the left. And it keeps going and going and going forever and ever and ever. Okay? But in terms of our company, the context of this problem, the range here now is going to be from 0, exclusive, because we don't want a planter box of 0, all the way up to 228. And that is inclusive, because we can get a planter box that has a volume of 228. Okay? So that's the inequality way. The interval way would be parentheses 0, oops, I almost put 20, parentheses 0, 228, and then a bracket. Okay? The x-intercepts, our x-intercepts again were 0, and 6, and 9. Okay? So at 0, that is the low end of our usable domain. Okay? That was the lowest that we could go, right? 6 is the highest we can go. So it's the high end of our usable range. And 9. Do I even care about 9? Nope, can't use it anyways. So this is not applicable. In terms of this problem. If this were just some random old function that we were graphing, which we will get to later on, okay, then yeah, we'll use it. Okay? But in terms of this specific problem, anything outside of my domain up here, between 0 and 6, means nothing to me, because we can't produce it. Okay?
Is, in this case, domain and range the same thing?
No, because range goes from 0 to 228. That's the outcome. Range is outcomes. Domain is what we're putting into our function to find the values. Okay? Okay? So, now, actually, let's save this one. We'll save this one for our warm-up tomorrow. Okay? Yeah, I like that. Okay? So, tonight's homework is actually on the cart in the back. It's the blue sheet. Okay? So you have a 2.1 blue sheet homework that you can go be picking up now. Thanks for playing along.